ठीक है सर, हो गया, स्टार्ट।
ओके सर। हाँ जी, रेडी? आराम से
ये केबल रह गया है अपने ख्याल से। केबल
Yeah, that was tutorial one, and now I have my file, but I need to go to that file.
Name of the folder.
India, but you can tell me where to get the folder. Where is it? It's not under Gyan, it's under Cruiser.
Okay.
I'm sorry, yeah.
हाँ जी.
This PC, okay. Okay.
This one is yours, sir.
Yeah,
Cruiser.
thank you, yeah. Let's see if we can.
Is it okay, sir?
Yeah, that's the third lecture. Yeah.
Okay.
Thank you.
Make it,
yeah.
sir, on full screen. Yes.
Okay.
Today we have an expert lecture of reliability engineering. This will be continued for first 2 hours, first 11 o'clock, and then you can class. The lecture is on reliability engineering. The lecture will be delivered by Professor Kailash Chandra Kapoor. He is Professor Emeritus at University of Washington, USA. Working at US for the last about 25 years at various positions.
in various universities. After doing his master's degree from IIT Kharagpur and PhD degree from Berkeley. So I think you will be benefited because it will be another kind of lecture for you. Though reliability is not a regular subject till third year. I think you may opt for final year, but still it's you can say of daily use. Lab engineering where we apply in all kind of real-life systems. You should keep patience and you should be attentive to this lecture. Okay? Sir, you can start now.
Good morning.
Good morning, sir.
So how's everybody doing? So we are learning, 3 things about engineering systems, the 3 R's, and they are reliability, robustness, and resilience. So we'll spend quite a bit time on reliability because that has been developed quite a bit for over 100 years. And big research was done after World War II. And then the area of robustness is only maybe about 30 some years old. So a lot of work was done in 80s, and resilience is relatively new concept. There are very few papers written on resilience. So if you ever want to do research or PhD, there are many opportunities to figure out how to develop engineering systems that are very resilient. Yesterday we gave you brief introduction to reliability, robustness and resilience. Today we look at lecture number 3 when you look at the course material, and the focus this morning is on reliability. So I can again briefly review what is reliability and then what is the role of probability and statistics in reliability. Why do we need probability and statistics? So yesterday we learned is that if you look at overall effectiveness of the system, people in the back can hear? Hear? Very good. So if you look at overall effectiveness of the system, how good something is, we also call it that is the overall quality of the system. So that is a function of all the infinite qualities that you design in a system. Some of these characteristics will impact reliability, some will impact robustness, some will impact resilience, safety, and so on. So the purpose of morning lecture is to talk about reliability. So yesterday we did that. We said that anytime you look at a word, a concept, you can always go back to the English language and say what's the meaning of that word. So the idea is that if we have a very precise definition, then we can communicate with each other. If I use a word, you have one definition, I have another definition, then we cannot communicate. So in order to communicate, the word that we use must have same meaning to all of us. If they have very different meanings, then there can be tremendous misunderstandings in the system. So you can see in T2 it says something reliable means that you can depend on something, and depending by definition deals with the future, not with the past, but deals with the future. So at this moment, you want to say like this sports person is jumping. Today, at this moment, they're saying, can I depend on these people? In couple of seconds, if they jump, other group will catch them. If they catch them, then the person says, oh, I can depend on these people. This group is reliable. So the word reliable in an engineering sense means is that if you design a system, it will do what it says it is supposed to do. So if I have this pointer, if I say, oh, how good this is, so if I click something here, I should see something on the screen. If it doesn't do that, then we say it is not reliable. But this is just a way of thinking. In science and engineering, we have to have a very precise definition of the word. One is the English definition, then one is the definition in science. So it says that for engineering and scientific purpose, the word reliability is something that you can precisely define what it means, how can you measure it, how can you evaluate it, how can you test it, how can you control it, how can you sustain it throughout the life cycle of the system. So we come up with a very precise definition. And because reliability is dynamic and you're dealing with the future, so you say that reliability is a characteristic. Remember yesterday we learned characteristic word is same as quality. And when you compress qualities from lower level to higher level, you can start relating to the needs of the customer, needs of the user. So with time, qualities change. Like the voltage of the battery in this projector, or voltage of the battery in my pointer, it will change with time. And as the voltage is changing, then if there is a metric for utility, then that utility will change over time. So we can come up with a typical definition for reliability. So the typical definition is because reliability deals with ability to depend. So it says reliability is defined as the ability. So somebody says, what is ability? So then we could say, what is the likelihood I can depend on you? So what's the likelihood something will do tomorrow? So if I have this pointer, I could say I have to teach this course until Friday. So somebody may ask, what's the likelihood it will work on Friday afternoon, right? So because this pointer will degrade with time, right? So then mathematically, I can calculate if I have engineering knowledge, whether it will work on Friday or not, whether it will work next week or not. It says it is, so we can substitute ability by the likelihood to quantify the degree of dependence. And that we quantify using the concept of probability. If I say probability is 1, then means this pointer definitely will work on Friday. If I say 95, that means there is a 5% risk it won't work. So maybe I should have a backup pointer in case this doesn't work. If the reliability is very low, then I'm very worried. Then maybe I have 2 or 3 or 4 backup pointers so that this product will work. And then you have to know what is the intended function, because as the intended function changes, the probability will change, right? And then you have to know for how long it has to perform its intended function, and then we have to know what are the operating conditions. So we can kind of expand on that. It says ability has many other things in it in addition to probability. So the idea is that even if I say it is probability, reliability is relative. Relative to the function, relative to time, because as time changes, the probability will change. So there is a very good probability this pointer may work next hour, but then next 2 hours it will be less, next 100 hours will be very less. So with time, probability or reliability number will change. And then it also changes based on the definition of failure. So question always is, what is failure? And every customer has a different definition for failure. So I could say, oh, this pointer already has failed. Maybe my red dot is not very visible. But with time, the red dot will keep on degrading, right? And every person can decide what is a failure. So why do you think the color is changing? Pardon? Maybe the voltage is changing, right? There may be some voltage surges in the system, right? So you can see things are very, very dynamic. And as the operating conditions change, then how good the projector rate will change, right? If suddenly there is a big surge, it could even harm or damage the projector. So reliability is a very relative concept. So this is a good teaching moment. It says how everything is dynamic. And then it is the job of the engineer to make sure that the system can perform its intended function under very dynamic conditions. So the idea is, like yesterday we learned about robustness, you don't want to complain about customers' use. You have to anticipate customers' use and then design the system so that it will still work under very, very dynamic conditions. And then you can do the same thing, because maintenance schedules are part of the operating condition. If you buy a car, like if you have all this equipment, and if you don't maintain it properly, it will fail very fast, right? So the idea is everything that is in the maintenance, how customer uses the product, is part of the operating conditions. So similarly, you can define the word maintainability, and you can define the word repairability. Then maintainability is related to resilience. Remember, resilience meant that how easy it is to sustain something, to restore the function of the system. So like you have a car, and if it breaks down, then you have to repair it, and then ultimately you want to restore the function of the car. If the car is very hard to repair and maintain, then it is not very effective. Then you cannot use the car. You say this system is not very resilient. If it fails, you cannot bring it back to the operating conditions. So maintainability is basically the same idea. You could look at the word maintainability in a dictionary. So maintenance says a continuing repair work, upkeep, continuation of something. If something is working, then how can I make sure that I can sustain it? And it says maintainability is to make something continue or to keep something in working order. So you want to maintain it, sustain that particular product. So similarly, we could define the idea of maintainability. So it says maintainability, just like reliability, is the ability, and that ability may be the probability, like we did in reliability, of a system to be retained, sustained, or restoring a system to a specified operating condition from an unacceptable condition. So reliability starts with success, and then you say how long it keeps on working. Maintainability starts with failure, and then it says how long it will take to fix something. How long it will take to fix something. So if you have a computer system, if you have a network, if you have a power system, so then you say how long it works. So if on the average it works for 10 hours, and then it goes down. So maybe it just goes down for 2 hours. So that means over 12 hours, it worked for, 10 divided by 12. Multiplied by 100, you could say, its availability is 10 over 12 times 100%. So that's the basic idea. So in maintainability, we go from unacceptable condition and in a given amount of time, and then we are able to restore it to the prescribed level of condition of the system. The basic idea is the same. So the idea is that quality and reliability and maintainability and resilience, these are all characteristics that you have to focus on throughout the life cycle of the system. So you could start like a life cycle. We could start with why there is a need for like this kind of a seminar, or why do we teach in engineering reliability. Typically, reliability is something that is common to all engineering field. It is not, doesn't belong to industrial engineering or mechanical engineering. Because what is reliability? To make sure that the things that we design, they work. Will you ever buy a product, a TV or anything that doesn't do what it says it's supposed to do? So nobody wants to work with, customers don't want engineered systems, buildings, infrastructure, power plants, that don't do what their job is. So then you teach reliability for software, you can teach reliability for hardware, right? So like all the equipment has a reliability. So reliability is a very, very basic thing. So whether you're an electrical engineer, mechanical engineer, chemical engineer, civil engineer, doesn't matter. You have to learn these basic ideas. So that's why, like in the United States, when we teach reliability engineering, we have students from all departments of engineering, not just from industrial and systems engineering or mechanical engineering. Because reliability is a very basic thing. Because you want to design things as an engineer, you want to design products that will do what they're supposed to do. And then we know that things do fail. So if they fail, you want to be able to fix them, restore them. So that's why maintainability is very, very important. So then you could say right from the beginning, we have to say what is the target for reliability, what is the target for robustness, what is the target for resilience. Then you come up with different concepts, and then out of many concepts you pick a certain design, then design, you do the development. So here you release the design. So once you release the design, its quality is fixed. So like we learned yesterday, quality is a function basically of the concept. If conceptually something is bad, there is nothing you can do to fix it. It will be very, very expensive thing to fix. So like yesterday we talked about society, political systems, social systems. If conceptually they are flawed, then people will always be struggling and struggling and struggling, and then they'll become very demotivated. And if they become demotivated, then lot of things, undesirable things will happen in society. So most important thing is not to fix problems, but more to be proactive and then upfront design the system so that 100 years from today, 1,000 years from today, or even if you're very short term, 1 year from today, 1 year is very short period, right? Most of us are worried about 1 hour from today, right? So if you think in that way, will I have food tomorrow? Can I, have a shelter tomorrow? Your thought processes will be very, very, very different. So you want to focus on how fundamentally in engineering you can change a system that is very reliable, that is very robust, that is very resilient. Because otherwise, if like we design buildings, we design bridges, we design power plants, and they don't work, that creates so much frustration in our society, right? If people are frustrated, that can never be very good for the quality of life in society. So these kind of principles are so basic, and every engineer has to learn about reliability, because if you don't understand reliability, things that you will design, they will fail. Your customers, people that you impact, they'll be very, very unhappy with you. And if their unhappiness long term has many bad consequences. So this is as basic as like life is. Making sure, because as an engineer, you are, servicing society. You are coming up with ideas, with products, with technology that will improve everyone's life. Our hope is that we are trying to improve everyone's life. Sometimes we are not very successful, but the objective is to improve everybody's life. And then in production, you want to be able to make sure that you can produce something that will meet the design requirements. And then you always evaluate in the field. Then if there are still failures, then you can give feedback and then continuously keep on improving the process. So yesterday we talked about weakness of feedback, right? What was the weakness of feedback? Anybody remembers? Yes, sir?
Process when the product is already in the market. And we are keep on producing the same, and that the defective products are already in the
market. Very good. So he said, like supposing somebody was making this pointer and maybe there are flaws in the design. They already made 1 million of them and selling them all over the world. Now these pointers don't work. They are flaws. Then so many people will be unhappy. You could get feedback, but people are already unhappy. So for this company, next year people say, oh, whatever this brand is, don't buy it anymore. So people will go to somebody else. And also you have done so much damage to society. You have created so much frustration for other people in society. So the wisdom was always not think about yourself, but think about how you are affecting somebody else. And then somebody else, and then somebody else. So that means focus on what is the impact of your life on other people in this world. I think all of you know that very old wisdom. So think about what are you contributing. Each person has a contribution. Most of us think we are just a drop in the bucket, right? So if in India there are 1.3 billion people, I say I'm 1 in a billion, what difference does it make what I do? But it makes a tremendous difference. If every drop thought it doesn't matter, then there won't be any bucket of water, right? So like you know that in our society here in India, if there is one child and takes out candy, has a small wrapper and just throws it away on the ground, he says, so what, one small piece of paper won't do much impact. But now 1 billion people start throwing wrappers, then what will happen to the whole country? It will look like a garbage dump, right? Then there'll be litter everywhere. That will pollute the environment. That will create health hazards. So enormous impact on society because everybody thinks they are a drop in the bucket. If every Indian says, oh, it doesn't really matter, I can't do too much. How can you do too much? And that is true. Every drop doesn't matter. But it has a tremendous impact on the system. Does that make sense? Most of you think you're just a drop in a bucket. No? Hopefully not. It's because each one of you can have a tremendous impact, not just on India, but on the whole world. So because once you resign yourself to think you're a drop in a bucket, then, it's not a very healthy situation. So you have a tremendous impact on society. And you don't want to create a culture. What is culture?
Tradition is followed continuously. One tradition will follow.
Continuously, sure, the way you think. So typically, even a simple idea, you say, oh, one simple idea, what difference does it make if I think something? But now if I have the same idea 1,000,000 times over my life, and then billion people think in the same way, very soon words, thoughts will become your habits. Habits will become part of your culture. Culture will impact the whole social, political system in this society. So every time you have a thought, it has a tremendous consequence. So it doesn't mean, so what difference does it make if I close my eye and think something? So we say, what difference does it make? It is just a thought. But thoughts result into actions. Actions become habits. Habits in future become culture. And then culture, you get stuck in it. Because then everybody wants to protect their culture. Then even they will teach you, oh, you should be proud of your Indian culture. But you don't want to be proud of the culture where you are stuck, that is inhibiting you from improving in the future. Make sense? Because it is common human nature, no matter what you have, you want to have pride in what you have, right? So that is a very basic instinct. Everybody will say, take pride in what you do. But you don't want to sustain things that are, we know based on the wisdom that we have, that are not very good, not very effective, that long term have very, very bad consequences. So all of these ideas, these simple ideas, not only you can apply to engineering, but you can apply to social systems, political systems, you can apply to your own personal life. Even if you think you're a drop in a bucket, question is, what kind of a drop are you? And then how can you improve the quality, productivity of your drop or of your contribution? So that's why you have to decide what is the definition of a failure. So a lot of this material is little more technical. So I think some of you may not be able to relate to, or it has very little meaning for you. But the idea would be that I can give you broader philosophical discussion so that something that we are presenting, it will stay with you for a long, long period of time. Even 50 years or 20 years or 10 years from today, you may remember some word that I used in these 5 days, and that could have some impact on your life. And you'll be amazed, most of us are not smart enough to know which thing will impact your life. You understand? So you will sit here and you say, oh, this guy is just saying a lot of nonsense. It doesn't matter to me. But you never know how that simple word will stay in your brain, and 10 years from today or 20 years from today, you'll be faced with some choices, and it will affect how you make those choices. And that's what teaching is all about. Teaching is not to help you get a job, but teaching is to transform you so that in future you can make impact on society. You have the right decision-making processes. You have the right attitudes. You have a way to think and think critically. You have the ability to question assumptions. So like we're talking of questioning assumptions, problem with culture and tradition is people get stuck. And you say, why are you doing something on Tuesday and not on Wednesday? Nobody has a good answer. They can come up with a story that why we protect our tradition. But you cannot get a scientific conclusion, a good empirical, why you're doing these things, right? So then all you're doing is you're sustaining things that have very little impact, or you are sustaining things that many times may be negative for society. So we won't go through like what's the meaning of the word failure or fault, but it is very, very important is that reliability will change as operating conditions change. So then the bottom line is that reliability is relative to function, relative to failure definition, relative to intended life, relative to the operating condition. So if I have this gadget and somebody hits it with a hammer, it will break, right? So if it breaks, then it doesn't work. That doesn't mean it is unreliable, because this was not designed to be hit by a hammer. So always remember is that, so like if this pointer, I abuse it, I throw it on the ground, then next minute it won't work. So that doesn't mean this was a bad design. It was designed to be treated well in certain conditions. And then you have to follow. That's why when you buy a product, they will tell you how to use the product, what not to do to the product, how to maintain the product. And if you don't follow all the instructions that the company gives you, the product won't work. So always remember is that reliability, safety, resilience, durability, they are relative numbers. So then we could say now we can, this discussion is mathematical. So if you don't follow the mathematics, don't worry. So mathematics is just a language. Just like I use English, or you can use Hindi or any other language. It is just a language to describe things, right? So we could say, oh, reliability is something that changes with time. And the way it changes with time is based on the models of probability. So then we can learn things in probability theory and then use that, all that knowledge to quantify reliability. So some of these symbols we can forget. So we could look at a very, very simple example. So supposing at time 0, I have n0 items. So let us say n0 is 100. So like I start in a company, they want to do testing. So they start with 100 products. And then we use these products. So as I use these products, some of these products will start failing, right? So maybe after 10 hours, 2 pointers have failed. Then after 20 hours, 6 pointers have failed. of course, by infinity, everything would have failed. So then at any point in time, we could say how many pointers are working. So S means success and F means a failure. So out of 100, I could say 80 are working at this point in time and 20 have failed. So 80 plus 20 is equal to 100. So then in a relative frequency sense, I say what is the probability that the pointer is working at time t? Or you say, oh, that's easy. So that is 80 divided by 100. So it is 0.8 or 80%. Then 80% is an index for reliability. Then I could say by 100 hours, maybe 70 have failed and only 30 are working. So then I say reliability at 100 hours is 30 which are working divided by 100 is 0.3. So probability always is a number between what and what? 0 and 1, right? So we normalize everything. So 1 is deterministic, 0 means, the likelihood something will happen is not there. We, at least mathematically, we cannot measure it. So that says that reliability at any point in time, then mathematical equation is very simple. It says number of successes divided by the number of failures. It's a very, very simple idea. So maybe with these slides, you can get a very simple, brief introduction to the field of probability. And we estimate probability using statistics. So probability and statistics is like a cyclical process. You start with a model. So model has no good unless you have empirical information to estimate the parameters of the model. So that's what science is all about. And then you do experiments, you collect the data, then you can estimate it. Now you have more data, then you can keep on modifying the model. So that's the basic scientific approach to improving things. So supposing we were looking at a product, and then here say the time to failure is in hours, and then we had 251 samples. So then we have like 11 different test groups, and then we say how products are failing over time. So we have now data for 251 products. So then we can make a table. So we could kind of compress the data. So if I give you 251 numbers, that is very hard to understand, right? So, but if then I could simplify these numbers, I could group these numbers, I can make a picture of these numbers. Then many students or people, they like pictures because picture is a good visualization. And then using that visualization, they have an idea of how good something is. So then by grouping, I could say right away in 10 hours, out of 251, 105 items failed from 0 to 10 hours. Then from 10 to 20, 52 things failed, and everything failed by, say, 150 hours. So that gives us some idea how reliable this product is. It says the likelihood this product will work for 150 hours is very close to 0. And then there is a very high probability product fails right away. And then it kind of decays exponentially. So you can make a mathematical model for how these products are failing. So then given this empirical data, we can hypothesize a theoretical model. Then I could say, oh, what is a good theoretical model that will fit this kind of histogram? So this is a decay that is something like exponential. It may start somewhere here and then it decays very, very fast. Then using that theoretical model, we can then predict in future how these products will fail. then I could say, if I was going to give warranty for this product, how many hours of warranty should I give? And if I wanted to communicate to the customer, what is the life of this product, then what number should I give? So anytime you buy many times a battery, how do manufacturers communicate life of the battery? What number they put on the battery, box of the battery? Have you seen that? If you buy a battery or you buy a light bulb, they say, what is the life of the light bulb? So what number do they put?
6 months.
Hmm?
6 months or a year.
6 months, but 6 months is what? Huh?
Time, sir.
No, but you know that I buy supposing the light bulb says 6 months, and I buy a light bulb, and it fails after 1 hour, then how would you feel? Pardon? What did you say? It's not reliable. But, you know, then the question is, what is the meaning of 6 months? See, like based on this example, the products can fail. Lot of products fail just within 10 hours, right? So if I was going to say, what is the life of this product, what number will I give?
Average.
Average. What is average?
Total number of.
So you take arithmetic mean, right? So what he says is that I could take 251, I could add them, and then divide it by n. Why do I take arithmetic mean? I could take geometric mean, harmonic mean. So there are all kinds of mean. So that is the field of statistics. What is a good statistic? You know the definition of the word a statistic? So a statistic is one word, one number that you get from 251 numbers. So you compress 251 numbers and then come up with one number. So the same idea is true. So like if I'm standing here, so somebody says, where is professor standing? So you want to give x, y, z coordinates in 3 dimensions, right? So you could give x, y, z coordinate my head, or you could give x, y, z coordinates of my feet. But which is the typical number you will give to say what is my location? So you use in like engineering the concept of center of gravity. Very good. So you could calculate my center of gravity, which may be somewhere here in the middle of my stomach, and you could say, oh, this is the location of the professor. You won't give coordinates of my finger or my head. So that is one number to communicate what is my location. So we can do the same thing. So for this particular product, we could calculate the center of gravity. So if you're going to guess where the center of gravity will be. 30 to 40. So he says, so center of gravity means is that if I have these weights, and then if I want to balance them, where will it balance? It's like you take courses in statics, right? A first moment. And so then where would it balance? So if it balances, say here, then I could say this is the average life. So the center of gravity mathematically is the first moment, right? That's how you calculate center of gravity. So then I'll say, oh, this device, so on the box, it will not say it is 30 days or 30 months. It will say average life is 30 months. Not the life is 30 months, not the minimum life is 30 months, but the average life is 30 months. And if I buy this product and if it fails after 1 hour, so I never told you it can fail in 1 hour, right? So if it fails in 1 hour and I complain, then the manufacturer will say, why are you so upset? You can go back and buy one more product maybe the next one would last 100 months. Then what is the average I experience? 1 plus 100 divided by 2. So that is 50.5. They say you should be very happy. I told you average was 30, but you're getting 50. So you shouldn't be unhappy. So the challenge is a lot of this thinking needs a high-level thinking, mathematics and training. Most of the people, in society, they don't have training in mathematics and so on. So you try to simplify things. Anytime you simplify things, you lose a lot. So a lot of information is lost. And then people have no clue how to use that number. So your box says 30, and if your product fails in 1 month, you are very, very upset. But company can never say it will last for 30 months, right? So 30 is an average over the whole population. So the center of gravity for the whole population relates to not to the individual, but to the whole group. So always remember, statistics has nothing to do with the individual. Like I ask you, how long are you going to live? So you know? Huh? Pardon? 70, 80 years. So you think he can say that? 200 years. He will live 200 years. So no one really knows how long you're going to live, right? Tomorrow, like yesterday, we talked about safety and how dangerous India is. So a lot of bad things can happen on the roads. So you can't know. But 80 or 70 years is a function of billion people. Statistics has nothing to do with the individual. It doesn't apply to the individual. No one person can live 70 years old or 80 years. The likelihood, mathematically, conceptually, probability is 0. Any number that you take. So then you can say, then based on these numbers, we can conceptualize a probability model. So here is an example of a probability model. So in this particular probability model, this axis is what we call as the probability density function. Then this axis is the time. And then it says this is the approximately like the shape of the histogram. And then this is how the products fail over time. So then at point here, this area on this side, like if I'm looking at this way, all the area on my right is the success probability. All the area on your left when you're looking at the screen is the failure probability. So failure probability at this point is this area, then this is, so like reliability here will be 100% because the total area under the curve is equal to 1. And then the reliability here would be like 0 because everything would have failed by that point in time. And then you can calculate the reliability by integration. So you could say at any point in time t, reliability is to integrate from t to infinity the probability density function. And then we can calculate the reliability function. So we can then kind of review that. We could say reliability at any point in time. I say, what is reliability at point in time t? So that means the system hasn't failed. So that the life of the product is greater than t. It has to fail some point in time, and then that time will be greater than t. So then the random variable is capital T. These are the specific values of time. So then I can calculate the reliability. So reliability, this probability is 1 minus the failure probability. Failure probability in statistics is called the cumulative distribution function. So then for many products, we can develop a concept called failure rate, or like in safety, we use the word hazard or hazard rate. And for many products, when you say how products fail over time, So failure rate means the number of surviving products, at what rate they fail in the next hour and the next hour and the next hour. So when you plot for many products the failure rate, you get a curve that starts at a high value, then it goes down, and then it stabilizes, and then it goes up. So towards here, then it will approach infinity. So it's like for human beings, so if you look at people, so in the beginning, many babies die. You understand? Yes, no? Most of you don't have kids, so you don't know. Why do babies die in the beginning? And what's the word we use? Infant mortality, right? So like if you go to a country, developing country, infant mortality is very high. So like in India, you could say how many babies die from 0 to 6 months. That number will be very high. Then to say how many people die from the age 40 and then 40 and 6 months. That number would be small. So infant mortality. So then in the last 100 years, one reason population in many countries is increasing is because we made tremendous progress to decrease the infant mortality. So like 100 years ago, if typical family, a woman may have 6 kids, and they say, oh, we don't know all 6 will survive or not. So maybe 4 will survive and 2 will die. And so many moms will die too during childbirth. But now with improvement in healthcare, that means we focus on the system. Let me see. I think there's certain uneasiness in the room. So you guys are restless. I suddenly, is it too much for you? No, not for you, but I find maybe people are a little bit restless. You want a break? Let me make sure. If we don't want to teach if people are restless. So you guys are okay? Follow this. It's not important to you. Is it, or you want to do something else? No, no.
Can continue 15 minutes more.
Oh, they have a class?
They have class at 11 o'clock.
11 o'clock, okay. So we can stop in another 10 minutes. And then you can have coffee or something, and then you can...
We can continue 10 more minutes.
10 more minutes, sure, sure. Okay. Thank you, thank you. But, rest and enjoy yourself. And maybe you can learn something. Even if you don't learn probability, you can learn something, how to think and how to articulate ideas to each other. So you can see, like in our society, one reason, like hundreds of years back, population wasn't growing very fast, but now it's growing faster. So now a woman doesn't have to have 6 kids or dozen kids. So if you have 2, that's good enough, because the likelihood something bad will happen is small. Same idea is true when we make products. So if you make a product, right away, if you test them, or if customers use the product in the beginning, everybody's okay? Yeah, okay. So in the beginning, failure rate will be very high. So a lot of things fail very fast, and then they stabilize it. So first question is, why do we have high infant mortality? Like for people, how come people right away die? And then what did we do over 1 century to prevent that babies are not dying?
Better healthcare.
Better healthcare, what does that mean? Vaccination, focus on prenatal care, educating moms, and then saying how
Healthy food for mothers.
Healthy food for mothers. So you focus on, you have better technology to deliver the baby, right? So you have hospitals. So typically in United States, even today, right in the beginning, the death rate is 4 times what it will be when you are, say, in middle age. So it's still very high. In India, maybe 10 times than what it will be in here. If you go to Africa, it will be very high. And then, of course, this rate will be very high at the end. Why will it be very high at the end? People grow old because we were not designed to live forever. Pardon? They lost their robustness, their immunity is not very good. So if older person, most of the older people, if you get infection, pneumonia, you will die fast. If you fall down, like old people always fall down, your hips break, then it's very hard to recover. But for a young person, it is very easy to recover. Yeah. So same ideas. Then there is a whole big field of science in reliability. Why do we have a constant failure rate, and how to design something so that we don't have wear out, and how to design something so that we have less infant mortality. So then we, as an engineer, now when I engineer things, I have to understand this curve. Just like for people, we have to understand this curve. In Western societies, this shape of this curve is the typical thing that we use in our bathrooms, and that is called a bathtub, right? Most of the bathtub is like this. So many times in the literature, when we talk about reliability, we say, oh, what is the bathtub curve? Because bathtub means that you start at a high level, then it kind of decays, then it is flat, right, in the middle, and then has the other side. So anytime if you read a reliability literature and they say, oh, this is the bathtub curve, so they are talking about the concept of failure rate. So then you can briefly, in your course material, later on you can study some of the descriptions that why do we have infant mortality. So you can see we use this word in engineering, we borrowed it from human beings. We understood infant mortality. So if you look at live animals, they have tremendous amount of infant mortality. Any insect, mosquito, they will have thousands of eggs and only a couple of them will hatch and become, and then whatever hatches also dies right away or somebody eats them up. So the amount of failure rate is tremendous early in the life of the product. These are like a couple of reasons. It says, why do we have infant mortality? It says we have infant mortality. Most of this is because there is a tremendous variation of the products. So if it's like in a class, supposing I teach, and I start with 100 students, and somebody says, oh, I don't follow what this professor is saying, or he's very tough. So 20 students, drop out. So that means the weak population has dropped out. So the rest 80 are better students, right? So that means if I looked at the average of 100, how good they are would be low. Because in my average, I have 20 weak students. But if you get rid of the 20 weak student, the average has improved. So that means the failure rate of the rest of the student will be lower. But the failure rate in the beginning was higher. So the same idea happens in life or with products. So anytime you make products, they are all not alike. Some are strong, some are weak. So weak things fail right away. So as soon as the weak things fail, the rest of the population is very good. So that's kind of the science behind why we have infant mortality. So in the end, it says, like in an engineering sense, it indicates the start of the wear out. So then the wear out is an important thing, because if you want to replace something, maintain something, overhaul something, then you want to recognize that you have very high failure rate. So your replacement schedules are based on the recognition of the failure rate. And then in engineering sense, we could say, why do we have wear out? So like with materials, there is wear, there is degradation, there is fatigue, there is corrosion, and on and on. So all of those things are reasons for wear out. Then we say, how can you optimize reliability? So you have to worry about all three phases of the life of the system. So any company has to worry about how to change the failure rate, how to test the products before we give it to the customer. Because if the failure rate is very high in the beginning, companies won't give you those products. So they will test them in the factory, because the cost to test in the factory is very small, right? But if they give it to you and then they have to come to your home and fix it, then cost is very high. So it is much better to debug it and test it and get rid of the weak items very early in the factory. So a lot of like engineering ideas, manufacturing ideas, maintenance ideas are based on understanding this bathtub curve. So these are just slides. This is mathematically how you develop it. That most of you may not be able to follow unless I teach you some differential calculus and on and on. So then you can see for that particular product, we can develop the failure rate. This is for the same product that we started, 251 products. So then you can see in the beginning failure rate is a little bit high, then it goes down, and then it goes up. So these are like some basic mathematical equations, how you can calculate mathematically. If you have a conceptual model for probability density function, then how you can calculate the failure rate. So then, like as an engineer, I could figure out how to decrease the failure rate. So then I could try to understand how do things fail in engineering. So in engineering, we use two concepts. We say something fails. So there are two variables. One is the strength variable. Strength is the ability to withstand the stress. And strength is a failure-inducing function. Stress is the failure-inducing function. Strength is the failure-resisting function. So if the stress will exceed the strength, then something will fail. So then we have two distributions. One is a distribution for load or stress, or there is a distribution for the strength. If you use higher safety factor, that means this distribution you can ship here, then the probability something will fail will be small. So when we design bridges, buildings, any kind of nuclear power plants, all the tools, machinery in a factory, we understand, we apply these principles, how to design products. We can communicate many other metrics for reliability. One of the things people use is percentiles of life. It says by what time 10% of the things fail, 20%, 50% things fail. 50% is called the median. You heard the word median?
Yeah.
What's the difference between median and the mean? I'm sorry? Mean?
Mean is the
Mean is the average of the number of...
Mean is the center of gravity, yeah, first moment. And median is?
the number which frequently occurs.
Yeah, so where 50% area is one side, 50% area is on the other side. Which one will be bigger, mean or median?
Medium.
No, you can't answer it. It will depend upon what is the shape of the distribution. So like in India, somebody says, what is the average household income? And other is, what is the median household income? Which one is bigger, median or the mean? In India, or even same thing in America. So you think one is a number, so that 50% of Indian households make less than that number. And other is a number that is the center of gravity for income. Which one will be bigger?
Median.
Sir, we have to find the data first.
No, data we know. Intuitively, all of us are smart enough to know what is happening in India, what is happening in America, and so on. So what happens is that supposing I have, say, 10 people, and one person makes $1 million, and the rest 9 people make, let us say, $100,000. So then, because one person made $1 million, and then I have to take the center of gravity. So you can see my center of gravity is like in physics, will be pushed towards that person. So average will be very high because in my numerator I put in million. But if other people are making less amount of money, median doesn't change. So typically in most of the societies in the world, average is very high compared to median. What is the difference between the average and the median? We use it to understand what is income distribution and why there is concentration of wealth. So like in India or in America, if you have Tatas and Birlas, because of their money, average will be very high. But median will be very, very small number because 50% of the population is hardly making anything. You follow? And more is the difference between the mean and the median that shows that this society is very unfair. Income is prosperity is not shared by everybody well. There is a tremendous concentration of wealth. And you can see a simple idea like that. Use it to understand how this society is functioning. So if you do that in India, the average will be very high compared to the median. In America also, average is high, but not as high as in India. So in India, top 1%, 1% still is very big of a billion plus people, they will have maybe more than 99% of the wealth, and rest of the population has nothing, right? So same thing in America, top 1% may have 60% of the wealth, and the rest 99% has small amount to share. So that shows how unjust society is. So you can develop very simple metrics like we are doing here to quantify the reliability. Reliability means the life of the product, how will make our customers happy. But you can apply it for any metric in society. So then these metrics can be calculated. Then our government has to come up with a policy how to change these numbers, right? So they'll say, oh, we'll tax all the rich people more and give the money back to the poor people. So every society has to figure out how to change that. And all those changes are based on this simple knowledge. So if you learn this, and if 20 years from today you'll become Prime Minister of India, hopefully you can benefit from it, right? You can figure out how to change our society and how come income disparities there in our society. How come small number of people have so much money and other people don't have much money? Make sense? So these simple statistics is very, very powerful to understand rational decision. If you don't understand knowledge, that's what happens in a developing country. People just make statements. and they have no rationale behind it. These are mostly emotional statements. They're just upset about society. They're saying we are poor people. How come people are so unjust? But they don't understand. They have no way to understand why that is happening. And then politicians don't understand how to change this system because they have no clue why things are the way they are. So that's the basic idea. So this mean, M means mean time to failure, is the first moment. Then we can calculate the second moment just like we do in engineering. Then I can calculate the third moment. I can calculate the fourth moment and fifth moment and so on. So these are like general equations to calculate all kinds of moment. Then each moment gives us some idea about what is happening. So like in India, is the third moment positive or third moment negative? So we can very easily calculate that in income. And then we say how positive it is. That means our distribution is very, very skewed. And if the distribution is skewed, I'll say this is not a good society. In this society, a lot of people will be suffering. So right from simple statistics, I can make a lot of evaluations. So we can stop right here. Thank you for listening. Thank you.
চাই আমি তোমাকে চাই, এক কাপ চাই আমি তোমাকে